Random bit flips and data corruption in storage mediums is a recurring issue, and no storage medium is totally immune to that problem. In this video, we will cover the correction of random bit flips in solid-state drive storage in computers. These random bit flips, which are not limited solely to the realm of SSDs, can be caused by noise disturbances. Our proposed solution is implementing the use of Reed-Solomon codes in these SSDs in order to correct the errors and preserve storage of devices used every day.
Storage mediums like SSDs are expected to work for a long period of time, and the chances of errors accumulating over time is high. There are no limitations on the type of data that can be stored on it, and it would be catastrophic to not correct errors in programs per se. We can encode the data before storage using Reed-Solomon codes, and it can be decoded such that they can retain the original values even in case of an error. The basic understanding of algebra and a sufficient understanding of basic linear algebra may help the viewer to appreciate the rest of the video to a greater degree.
We will now be going over solutions to our problem. Alrighty, so for our solution we will first define a few parameters or variables to kind of give an overview of what codes do generally. So the first parameter we'll define is k, which is the dimensions or the message length of a message. So the basic idea is that we have a message with a certain set of symbols, and then we add redundant or extra symbols to that message, which then we can kind of use to retrieve the original message per se in the decoding process. So we have n, which is the block length, or also the length of the code word. So how, like I previously stated, how it basically works is that we have a message of length k and it's mapped to a code word of length n. And then we have another parameter or variable q, which is the alphabet size. It's the number of symbols in the code that is, the number of symbols in the code that is both messages and code words contain the same set of symbols. And for our solution, we will use a family of codes named Reed-Solomon codes for encoding and decoding the data. So here is a basic overview of Reed-Solomon codes. The general idea behind them is we take a message of length k, and it's mapped to a unique polynomial f of x, which has a maximum degree of k minus 1. So to encode the message, we take n values, a1 through an. We then evaluate the polynomial f of x for each value, and then the resulting set of values is the code word. So given this general definition, we can construct something called a generator matrix. Now what a generator matrix will do is it will take a message and we will multiply that message by the matrix. That will then produce a unique code word for that message. So given this general definition, G can be constructed in this way, where we have all of our evaluation points as the columns, and then we just raise them to the 0th power, the 1st power, the 2nd power, all the way up to the k minus 1 power. It's pretty much the same process. You can see the relation here. It's just kind of a different order. So given that, we will now show what our generator matrix is and then explain some other properties that it has. So for our general solution, we picked n to be 11, k to be 4, and then we picked the set of evaluation points 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Given that this is the generator matrix that is constructed, it is important to note that all operations, addition, subtraction, multiplication, whatever it may be, it won't produce symbols outside of the set of symbols. So for say, like in this case, we picked 11. We couldn't possibly have a number within either of these matrices that would be greater than 11. So this is G. It's a 4x11 matrix, so this is the general construction based off how it was defined on the previous paper, and this is H. So H is a parity check matrix. What this does is that it takes a code word produced by G, and then we multiply that code word by H. If the multiplication produces an all-zero vector, then we know that there weren't any errors during transmission, storage, whatever it may be. Contrary to that, in the case where multiplication by the code word produces something other than the non-zero vector, we can determine that an error has occurred, and then we can go through and do some error correcting. So in order for G to produce unique code words given a message, so like it's a one-to-one mapping for a message to a code word based on multiplication. So basically when we multiply G times M, we want to ensure that the code word produced is unique and that it's unique for every message. So in order to show this, G needs to be full rank. Essentially what that means is you row reduce the matrix down to its most reduced form, and then the number of non-zero rows is equivalent to the rank of the matrix. So we will show a quick proof which kind of just explains how, or shows why it is full rank. So this is our original matrix. You can apply your favorite row reduction algorithm. Gaussian elimination of course works well, and then we get down to the point where we have the identity matrix in the first 4 columns, and then just a bunch of non-zero entries in the last 7 columns. And then obviously, since we have the identity matrix present, it can't be the rows can't be entirely 0, and since there are 4 non-zero rows, the matrix has full rank, and it satisfies the constraint that the rank of G is equal to K, which is essentially the constraint for a matrix being full rank. Now, given our parity check matrix, we have to also ensure that this parity check matrix is orthogonal to G. In other words, it's essentially a perpendicular plane. So what we do is we take G times H transpose, so we take the transpose of the matrix, and then we multiply, in this case, the rows become columns, and then we take each column and then multiply it by G, and then it should produce an all-zero matrix, and then that satisfies the constraint that G and H are orthogonal. So the proof goes as follows. This is just taking G times H transpose, and for the sake of brevity, this would just be lines of operations otherwise. We only showed the first few. You can go ahead and verify the rest yourself if you like, but it will hold. So these are the results of multiplying the first row or the first column in H transpose times the first row in G. So we take that sum, or the inner product, and then all operations are done mod 11, since we have to ensure that the symbols produced are no more than the symbols in the alphabet. So the sum's up to 11, and then we take 11 mod 11, which is 0, and then we can show the next operation of multiplying the first column in H times the second row in G. The inner product comes to a value of 55, and then we take 55 mod 11, which is 0, and then you can go through and then manually verify the rest of this yourself if you like, but this will produce an all-zero matrix. Given that, we want to know how many errors can the code correct. It's a known fact that the codes can correct up to, or for Reed-Solomon codes, they can correct up to n minus k divided by 2 errors, and then we round that value down to the nearest integer. So in our case, our code has block length 11, dimension 4, and then we take 11 minus 4, divide that by 2, that gives 3.5, but we round down to the nearest integer, which gives us 3, and then we have a total of 3 errors that our code can correct. And that is our solution to the problem.